So me and Hassan made a science fair project, and so our problem was basically that streams and rivers today have heavy metals that are very toxic and have really harsh effects. Some of these effects include reduced growth and development, cancer, organ damage, nervous system damage, and in extreme cases, death. In Flint, as you all know, there's a heavy metal problem with lead, but this especially affects the children. So it has the same effects as anyone else, except there's memory impairment and there's behavioral problems such as hyperactivity and aggressiveness. Heavy metals can also affect aquatic life and have an effect on their behavior, which they can disrupt their sensory systems, their predator avoidance, and migration. These toxic metals come from mining, farming, manufacturing operations, and municipal or industrial wastewater releases. It can also come from corrosion of pipes. So the essential questions / purpose. So we wanted to see if we could make a filter out of using cellulose nanofiber to filter out these heavy metals. And we used copper nitrate because it was blue, and we could see the results.
Now the reason why we chose copper nitrate is because it's colored. So we used Beer-Lambert's law to be able to measure the concentration before we put it in a filter that we designed and after we put it into a filter that we designed. So we used pipettes, spectrophotometers, cuvettes, copper nitrate, and a colorimeter. So the actual scientific procedure was about 16 slides, but I'm not going to go over all of that.
Thank you.
So I'm gonna give a basic rundown. So basically, we took a cuvette of copper nitrate, we put it into a colorimeter, and we measured the optimal absorbance at what nanometer it would have an optimal absorbance. And then we created a calibration curve using Beer-Lambert's law. So we had known concentrations of copper nitrate, and then we created a calibration curve, and we had an R square value of 0.99 on it. And this is what we would use to find the concentration of sample of copper nitrate after you put it through our design filter system. So our design filter system was basically just a funnel with 3 pieces of filter paper, and then we took a known concentration of copper nitrate and shook it vigorously with an amplitude of about I believe it was 10 centimeters both ways. And we did that for about 40 seconds. And then after that, we put it into our filter system, and then we collected what was left. And then we got that sample, we put it back into a spectrophotometer. We put it at 650 nanometers, which was what our optimal absorbance was at. And then we got a concentration using this very graph. So once we got our sample outside of the filter, we got its absorbance, and you can literally just take a line and then you would find its ending concentration. So you would know, hey, the sample concentration that we put in was 0.5, but then after we took it out and we got a certain absorbance reading from a spectrophotometer, we can go back and know, okay, now it's 0.3. What that means was that copper was taken out. So our legitimate results. This is a graph with 5 trials, all with 0.1 molar of copper nitrate. And as you can see, the blue is what we started off with, and the red is the result we got. And in every single case, we reduced the concentration by over 76%. Now this was only at 1 concentration, so we did it at multiple concentrations. We had a 0, we just had distilled water put through. We had a 0.05, we had a 0.1, 0.2, 0.35, and 0.5 molar solutions put through this filter system. And the percent change is on that graph. It was all above 60%, and this was throughout all of these concentrations. And when we graph the change of the change you got from the filter, we got this graph, which basically means that within the range of concentration that we tested on, it was basically constant. We had an R-squared value of 0.98, which meant that the amount it decreased our concentration-wise was relatively constant. Now, if past this certain concentration, we didn't test it, so we can't know that after this, will it still have that same constant effect. But between the range that we tested it on, it did. So, and a 0.98 R-squared value is pretty good. So, so our purpose was to see if our filter system would be able to decrease or take out heavy metals from water. And we were able to see that in our case, we were able to take out copper from copper nitrate. Now this doesn't mean that we can take out any heavy metals. We would have to test it further and with those heavy metals. But for copper, we've got this, and we'd have to further analyze and do more experimentation before carrying it out even more.
So these are our future plans. So if I come here, so here we have a stream, and so the runoff will come here. And so these right here are cattails, and cattails have been proven to absorb contaminants, so we'll go through those. And then here we have this sort of turbine that's filled with cellulose nanofibers, and when the water goes through, the water and cellulose nanofiber will, so everything will be shaken vigorously, and then it will come out clean. And then here, we thought like, oh, we could also use this at home as a cheap filter, because like in Flint, a lead filter is like $800. So we want something cheap that anyone can afford. So basically, we'd have this jug of water, say, and we put the filter on the top here, and it could go through this mini turbine maybe, and it, like I said before, it would just shake the cellulose nanofibers and the water vigorously, and it would come out clean.
Now this is after years of experimentation, and what if we did that in the future. So right now we wouldn't be able to do this, but in the future if we were to.
The last thing